application of urban extreme temperature predictions with satellite and ground observations in Austria.
Thank you for the introduction. My name is Sandro Oswald from the Geosphere Austria, previously called the ZAMG in Austria, and today I'm going to talk about our new model system to predict extreme temperature events and how to verify it with ground and satellite observations. Why we'll do it, our motivation is, of course, the air temperature anomalies, which occur more often in Europe, and people in cities are more affected, and we want to reduce the mortality rates and create a new warning system. And if you see the current warning system from Meteor Alarm, you see only districts in cities can be chosen and have no information about the special distribution of air temperature inside the city. So what we want to do, we want to set up a new air temperature prediction system for urban environments and use therefore the arome coupled with surfax, and the output should be the basis for extreme weather temperature prediction system and the thermal stress warning system. And we want to get from the arome prediction system at 2.5 kilometer to something like that. So how do we do it? We use surfax called Surface Extending Z, developed by Meteo France, as you know, maybe of you, and couple it to arome. And the advantages of this is the possibility to have sample runs, and we also have the ability to use a physical downscaling instead of a statistical, detailed land cover information, and the possibility of a height correction. For the land cover information, we want to improve the current situation. So we have here our EcoClimUp, which is normally used for surfax, and we want to use instead Atlas from 2018. But we also want to know the properties of each class. Therefore, we use the Land Information System Austria, which is a very high resolution land cover information. And from that, we get the properties of each class, like the fraction of buildings, the height of fraction, and the fraction of vegetation, and so on. And we also improve the cells inside. So we want to use a weighting scheme. So we calculate each percentage of each class in each grid cell. So we have the weighting of each class. So for example, the urban areas, 50%, then 25% vegetation, and 25% of water. And here is the result, compared EcoClimUp to the new system. So we see EcoClimUp has only 1 point for whole Vienna, for the surface cover class streets and tracks. And here on the right side, we see the new information and the percentage of streets and tracks. And also we have additional parameters as the NDVI, or the area index, and we also calculated the visible albedo from Landsat 7 bands as an average from 2018 to 2021 during the summer season. And all this information got now in our diurnal simulation. So we have every day an operational run. This operational run is finished at 5 UTC, and we have a time resolution of 30 hours in the future, and the results look like that. So we see a clear improvement of the special distribution of the air temperature inside the city, but we also see a strong divergence or strong boundary between the temperatures, because we have no horizontal attraction between the cells. And this simulation starts every 6 hours, so we have in sum 4 simulations per day, and we also include water surface temperatures from the Danube, which is updated every 10 days. So comparison with the ground observations. we have several operational weather stations in Vienna, and some 9. And if we compare it as a hourly mean bias, then we see Surfax in blue is slightly better to the weather stations than our Rome itself during the night. But during the day, we have an overestimation up to 1.6 Kelvin. So we see higher resolution means not better results, but in the RMSE, we have similar results. And we have also the opportunity to use NetAtmo, so private weather stations. In Vienna, we have, after the quality control, about 1,500 stations. And we see here on the bottom, in the black, the NetAtmo stations, and in blue, the operational weather station. So it's quite good for this specific time period. And if we compare Surfax to NetAtmo, we see a similar effect. So Surfax has, again, a slightly overestimation up to 5 degrees Celsius during the day. But during the night, we have very good results. And we see also here the special distribution from Vienna. It's around 0 during the night, and during the noon, we have this overestimation. But it's better to have higher temperatures in summer than less. And we want to also use satellite observations, compare them. Therefore, we use the method of Benjamin Bechtel from 2015. He used annual cycle parameters. So we calculated the LST over a time period for whole Austria, and we get therefore the mean annual surface temperature and the yearly amplitude. And then we want to downscale MSG measurements from 1 kilometer to 100 meter and compare them to Surfax. And we see here our results from the mean annual temperature, MUST and TEST for Austria. And we also use the other predictors for downscaling as the Sentinel-2 composite, digital elevation models, vegetation indices, and tree cover density from Copernicus. So in sum, we have 10 predictors with the random forest regression to downscale the LSD. And let's see as a result from last year in July. We see here on the left the 1 kilometer measurement, and on the right the 100 meter. So we can compare the surface temperature calculated in Surfax with these downscaling measurements. And if we use a period, for instance, a cold wave this year in February in Vienna and a heat wave last year, then we see in the dashed line is Surfax and the solid line is the LSD downscaling. So we see the winter, Surfax underestimates the minimum temperature, and in the summer season, Surfax overestimates the surface temperature during the day. So we see also here this effect of the overestimation during the day, and we think we have a problem with the capabilities or the thermal conduction from the buildings. So that's why we have this overestimation through the day. So what we do, or for summary, we saw that the coupling of Surfax and the Rome does work well, and the results during the night are pretty good. We have a slightly overestimation during the day, and we also can verify these temperature predictions with LSD downscaling. And further steps, we want to calculate the thermal comfort. As we heard already in the morning, that the maximum of air temperature is not the same as the maximum from thermal comfort. And we want to compare also the LSD downscaling with satellite measurements as the echo stress on 70 meters. And as the last part, we want to use the LSD downscaling to assimilate the Rome prediction system, the ground assimilation, and also to compare them with Surfax and with machine learning methods. So thank you, and looking forward for questions.
Thank you so much. We have time for questions. Any questions? I have a question. How do you see this translated into some policy action or decision making? Because you're looking at extremes, right? So
Yeah.
are you working with the city on
Yeah,
how
we
to translate
work
this?
with the city a lot there. First, the primary we want to use this as a monitoring system.